Let's look at the cross-section of a solid shaft. By the way, in this course, we limit our discussion to continuous, cohesive materials only. This means that the material properties are uniformly distributed within the member, and there is no void, disconnection, or breakage in the material. From the statics course, we learned that there can be a maximum of 6 independent internal reaction components, 3 internal forces, and 3 couple moments. I'd like to remind you once again that if you are not sure how to determine the internal reactions, you need to review statics. We also learned from statics that these 6 are in fact the resultant forces and resultant couple moments summarized about the x, y, and z axes respectively. The actual internal forces are distributed throughout this cross-section. We will learn more about how the internal forces are distributed later in this course. Normally, these resultant internal reactions are placed at a special point, the centroid point of the cross-sectional area. Let's look at a very small area, a differential area, delta A, on this cross-section. And the force acting on this small area is delta F. Let's zoom in on this area. This force delta F can be resolved into 3 components along the x, y, and z directions respectively. Again, the force component along the y direction is the normal force, and the x, z components are shear forces. When this area delta A approaches 0, the area becomes a point, and the normal stress sigma at this point is defined as delta Fy over delta A. And the shear stresses tau at this point are defined as the force components along the x and z directions over delta A, respectively. Note that the shear stress has 2 subscripts. The first subscript indicates what surface it is. Surfaces are defined by its normal direction, in this case the y direction. Then the second subscript indicates the actual direction of the shear stress vector. Since stress is defined as a force over area, in the SI unit system, its unit is Newton over meter squared or Pascal, and in the US customer unit system, its unit is pound over inch squared or PSI. Therefore, for an infinitesimal area delta A on this cross-sectional surface, it could have a maximum of 3 independent stress vectors acting on it, a normal stress sigma and 2 shear stresses tau, corresponding to the 3 internal forces. But does a particle only have one surface? Normally, a particle is represented by a cube with infinitesimal sides. We all know that a cube has 6 surfaces: top, bottom, front, back, left, and right. Therefore, on each surface there is a normal stress sigma that is perpendicular or normal to it, and also 2 shear stresses tau that are tangential to it. We call this the general state of stress of a particle. If you recall what I mentioned in the introductory video for this course, in mechanics of materials, we still only study objects that are in equilibrium. Therefore, the equilibrium conditions still apply. Derived from the equilibrium conditions, we can have the following 2 conclusions. First, the normal stresses along the same direction must be pairs with equal magnitudes and opposite directions. Secondly, the shear stresses within the same plane, in this case the YZ plane, must have the same magnitude. Also, their directions must follow this rule, that the 2 adjacent shear stresses must be either towards each other or away from each other. And this is called the complementary property of shear. Therefore, the general state of stress of a particle can be characterized by 6 independent stress components. There are 3 normal stress components along the x, y, and z axes respectively, sigma x, sigma y, and sigma z, and 3 shear stress components within the xy plane, xz plane, and yz plane respectively. When we reduce our 3D analysis to 2D analysis, in other words, we focus on the state of stress within only one plane, in this case the XY plane, then there are only 3 stress components: the 2 normal stresses along the XY axis and the shear stress within the XY plane. And this is called the planar state of stress. Stress is a variable. Here, let's look at the normal stress. It changes with location across the cross-sectional area. The integration of the normal stress over this area equals to the normal force. Stresses are tensor quantities. Therefore, the actual normal stress distribution is complicated and also beyond the scope of this course. Instead, an approximation using the average normal stress is generally sufficient. The average normal stress is simply defined as the total normal force over the total cross-sectional area. This corresponds to an idealized uniform distribution of the normal stress over this cross-section. This means that we assume the normal stress is the same everywhere on this cross-section. Similarly, the shear stress in the x direction also varies with location, and its integration over the cross-sectional area equals to the shear force Vx. And again, for convenience, we define the average shear stress as simply Vx divided by the total area, and that also indicates an idealized uniform distribution of shear stress. And same thing for the shear stress in the z direction. The average shear stress in the z direction is defined as shear force Vz divided by the total area. Now please answer the following questions.